Deep Learning Foundations and Concepts 1. The Deep Learning Revolution. 1.2. A tutorial example. Introduction for the newcomer to the field of machine learning. Many of the basic concepts and much of the terminology can be introduced in the context of a simple example involving the fitting of polynomial to a small synthetic data set. This is a form of supervised learning problem in which we would like to make a prediction for a target variable given the value of an input variable. Synthetic data, we denote input variable by x and the target variable by t, and we assume that both variables take continuous values on the real axis. Suppose that we are given a training set comprising n observations of x written from x sub 1 to x sub n, together with corresponding observations of the values of t, denoted from t sub 1 to t sub n. Our goal is to predict the value of t for some new value of x. The ability to make accurate predictions on previously unseen inputs is a key goal in machine learning and is known as generalization. We can illustrate this using a synthetata set generated by sampling from a sinusoidal function. Figure 1 shows a plot of a training set comprising n equals 10 data points in which the input values were generated by choosing values of x sub m for n equals 1 to n, spaced uniformly in the range 0 and 1. The associated target data of values were by first computing use of the function sine to pass for each value of x, and a small level of random noise by a Gaussian distribution to each such point to obtain corresponding target tau t sub n. By generating data in this way, we are capturing an important property of many real-world datasets, namely that they possess an underlying regularity which we wish to learn, but that individual observations are corrupted by random noise, linear models. Our goal is to exploit this training set to predict the value t hat of the target variable for some new value x hat of the input variable. As we will see later, for the training data, this involves implicitly trying to discover the underlying function sine to popax. This is intrinsically a difficult problem, as we have to generalize from a finite data set to an entire function. Furthermore, the observed data is corrupted with noise, and so for a given x hat there is uncertainty as to the appropriate value. Probability theory provides a framework for expressing such uncertainty in a precise and quantitative manner, whereas decision theory allows us to exploit the deistic probability representation to make predictions that are optimal according to appropriate criteria. To start with, however, we will proceed rather informally and consider a simple approach based on curve fitting. In particular, we will fit the data using a polynomial function of the form where m is the order of the polynomial. The polynomial coefficients are collectively denoted by the vector w. Note that, although the polynomial function y of x and bu is a nonlinear function of x, it is a linear function of the coefficients w. Functions such as this polynomial that are linear in the unknown parameters have important properties as well as significant limitations and are called linear models. Error function, the values of the coefficients will be determined by fitting the polynomial to the training data. This can be done by minimizing an error function that measures the misfit between the function y of x and w for any given value of w and the training set data points. One simple choice of error function, which is widely used, is the sum of the squares of the differences between the predictions y of x of mbu for each data point x sub n and the corresponding target value t sub m given by, where the factor of 1 over 2 is included for later convenience. We will later derive this error function starting from probability theory. Here we simply note that is a non-negative quantity that would be 0 if and only if the function y of x and w were to pass exactly through each training data point. The geometrical interpretation of the sum of squares error function is illustrated in figure 1.5. We can solve the curve fitting problem by choosing the value or w for which e of w is as small as possible. Because the error function is a quadratic function of the coefficients w, the training data, its derivatives with respect to the coefficients will be linear in the elements of w, and so the minimization of the error function has a unique solution denoted by w asterisk, which can be found in closed form. The resulting polynomial is given by the function y of x and w asterisk. Model complexity. There remains the problem of choosing the order m of the polynomial, and as we will see, this will turn out to be an example of an important concept called model comparison or model selection. In figure 1.6, we show 4 examples of the results of fitting polynomials having orders m equals 0, 1, 3, and 9 to the data set shown in figure 1.4. Notice that the constant m equals 0 and first order m equals 1 alone give poor fit to the data and consequently poor representations of the function sine 2 pay x. The third order m e equals 3 polynomial seems to give the best fit to the function sine 2 po x of the examples shown in figure 1.6. When we go to a much higher order polynomial m equals 9, we obtain an excellent fit to the training data. In fact, the polynomial passes exactly through each data point and EW asterisk equals 0. The fitted curve oscillates wildly and gives a very poor representation of the function sine 2 px. This latter behavior is known as overfitting. Our goal is to achieve good generalization by making accurate predictions for new data. We can obtain some quantitative insight into the dependence of the generalization performance on M by considering a separate set of data known as a test set, comprising 100 data points generated using the same procedure as used to generate the training set points. For each value of M, we can evaluate the residual value of E of W asterisk given by 1.2 for the training data, and we can also evaluate E of U asterisk for the test dataset. Instead of evaluating the error function E of W, it is sometimes more convenient to use the root mean as RMS square or def. Graphs of the training set and test set RMS errors are shown for various values of M in figure 1.7. The test set error is a measure of how well we are doing in predicting the values of T for new data observations of X. Note from figure 1.7 that small values of M give relatively large values of the test set error, and this can be attributed to the fact that the corresponding polynomials are rather inflexible and are incapable of capturing the oscillations in the function sine 2 px. Values of M in the range 3 less than or equal to M less than or equate give small values for the test set error, and these also give reasonable representations of the generating function sine 2 px, as can be seen for M equals 3 in figure 1.6. We can gain some insight into the problem by examining the values of the coefficients W asterisk obtained from polynomials of various orders. As shown in table 1.1, we see that as M increases, the magnitude of the coefficients typically gets larger. In particular, for the M equals 9 polynomial, the coefficients have been finely tuned to the data. They have large positive and negative values so that the corresponding polynomial function matches each of the data points exactly. But between data points particularly near the ends of the range, the function exhibits the large oscillations observed in figure 1.6. Intuitively, what is happening is that the more flexible polynomials, larger values of M are increasingly tuned to the random noise on the target values. For insight into this phenomenon can be gained by examining the behavior of the learned model as the size of the data set is varied. As shown in figure 1.8, we see that for a given model complexity, the overfitting problem becomes less severe as the size of the data set increases. Another way to say this is that with a larger data set, we can afford to fit a more complex in other words, more flexible model to the data. One rough heuristic that is sometimes advocated in classical statistics is that the number of data points should be no less than multiple of 10, say 5, or 10, the number of learnable parameters in a model. However, when we discuss deep learning later in this book, we will see that excellent results can be obtained using models that have significantly more parameters than the number of training data points. 1.2.5 Regularization. There is something rather unsatisfying about having to limit the number of parameters in a model according to the size of the available training set. It would seem more reasonable to choose the complexity of the model according to the complexity of the problem being solved. One technique that is often used to control the overfitting phenomenon as an alternative to limiting the number of parameters is that of regularization, which involves adding a penalty term to the error function 1.2 to discourage the coefficients from having large magnitudes. The simplest such penalty term takes the form of the sum of the squares of all of the coefficients, leading to a modified error function of the form where u vert pair square and the coefficient lambda governs the relative importance of the regularization term compared with the sum of squares error term. Figure 1.9 shows the results of fitting the polynomial of order or m equals 9 to the same data set as before, but now using the regularized error function given by 1.4. We see that for a value of ln lambda equals minus 18, the overfitting has been suppressed, and we now obtain a much closer representation of the underlying function sine 2x. If, however, we use too large a value for, then we again obtain a poor fit, as shown in figure 1.9 for ln lambda equals 0. The corresponding coefficients from the fitted polynomials are given in table 1.2, showing that regularization has the desired effect of reducing the magnitude of the coefficients. The impact of the regularization term on the generalization error can be seen by plotting the value of the RMS error 1.3 for both as shown figure 110 as shown in lambda sets against training and test sets eros air view. We see that lambda now controls the effective complexity of the model and hence determines the degree of overfitting. 1.26 Model selection. The quantity lambda is an example of a hyperparameter whose values are fixed during the minimization of model parameters ABU to determine the error function of the value. We cannot simply determine the value of lambda by minimizing the error function jointly with respect to AU and say that to lambda overall is 0 and an odal or 0 training error fitted lambda approaches to error, and since this will lead. Similarly, the order m of the polynomial is a hyperparameter of the model, and simply optimizing the training set error with respect to m will lead to large values of m and associated overfitting. We therefore need to find a way to determine suitable values for hyperparameters. The results above suggest a simple way of achieving this, namely by taking the available data and partitioning it into a training set used to determine the coefficients u, and a separate validation set, also called a hold-out set or a development set. We then select the model having the lowest error on the validation set. If the model design is iterated many times using a data set of limited size, then some overfitting to the validation data can occur, and so it may be necessary to keep aside a third test set on which the performance of the selected model can finally be evaluated. For some applications, the supply of data for training and testing will be limited. To build a good model, we should use as much of the available data as possible for training. However, if the validation set is too small, it will give a relatively noisy estimate of predictive performance. One solution to this dilemma is to use cross-validation, which is illustrated in Figure 1.11. This allows a proportion s minus 1 over s of the available data to be used for training, while making use of all of the data to assess performance. When data is particularly scarce, it may be appropriate to consider the case s equals n, where n is the total number of data points, which gives the leave one out technique. The main drawback of cross-validation is that the number of training runs that must be performed is increased by a factor of s, and this can prove problematic for models in which the training is itself computationally expensive. A further problem with techniques such as cross-values separate data to assess performance is that we might have multiple parameters for a single model, multiple complexity hyperparameter that date hyperpar instance. There might be several regularization hyperparameters. Exploring combinations of settings for such hyperparameters could, in the worst case, require a number of training runs that is exponential in the number of hyperparameters. The state of the art in modern machine learning involves extremely large models trained on commensurately large data sets. Consequently, there is limited scope for exploration of hyperparameter settings, and heavy reliance is placed on experience obtained with smaller models and on heuristics